Thanks. All right, module 9, parallel processors. Again, I'm referring to the chapters we used because a lot of figures are used in this module that's actually coming from the book. So I'm citing the references in the beginning. We have Computer Organization and Design, Chapter 6. We have Computer Architecture and Quantitative Approach, Chapter 4. And then we have Digital Design and Computer Architecture, Harris and Harris, Chapter 7. So I actually use a lot of materials from Harris and Harris' book for this chapter. You should be able to find it online, but I just wanted to cite them before starting the module. So we covered Amdahl's law last time, and the whole point of using Amdahl's law was to emphasize that everything we say after this point about the parallelization, we should always have it in mind that how much of the workload can be parallelized, how much of that can be improved. So that's just avoiding a possible fallacy that if we have improvement, if we have parallelization, it's gonna, no matter what kind of code you have, it's gonna make it faster. So that's not the case. There are many examples that your code cannot be parallelized, and no matter how many cores you have, whether you use GPU or not, it's not gonna make it faster, right? That was why we started with Amdahl's law, but now we're gonna talk about parallel processors. Okay, so I'm starting with a very important hardware categorization that is based on the Flynn's taxonomy. This is actually, there's a Wikipedia page for that, and it talks about this kind of the Flynn's taxonomy and how to categorize different hardware and computer architecture based on the taxonomy. So you can get more information from that in this page, and it provides a lot of good information. But I'm going to provide a brief description about each of these categories that we have for computer architectures. So far we talked about the single instruction, single data computer architectures. Everything we talked about in MIPS had single data stream and single instruction stream, right? The whole categorization is based on, by the way, it's based on the number of instruction and data streams that you can have. So this we have covered. MIPS is a good example. More practical hardware, which is pretty old too, is Intel Pentium 4. It was also a single instruction, single data. It started in 2000 and they discontinued it in 2008. So this is pretty straightforward. You have one instruction stream and one data stream, and you're familiar with that. Now, the next type of architecture we can get is single instruction stream, multiple data streams. So I want to go back and forth with this, but just have these figures. So single instruction stream and multiple data. What it means is that you're running the same instruction on different data. So a good example of this is systolic array, TPU. How many of you have heard about TPU? That's the processing unit. Okay, so TPU is a good example of single instruction, multiple data architecture. You do the same multiply and accumulation operations, which is the same instruction, but you use different inputs. So every time you multiply two different values, which is weight and input in case of machine learning, for example, and you do the same multiply and accumulation. This means that we have a single instruction stream, as you can see here, running the same instructions, but you have multiple data to work with. Okay. So the next type of architecture is multiple instruction, single data stream. So you can look at it here. It's different instruction on the same data. So this doesn't happen that often. This is not a very common computer architecture because you don't really do different computation on the same data. Unless for applications like space exploration, mostly it's for fault recovery and recognition. So let's see if I can find check something here. I'm sorry. I'm not sure this is the most recent version of the PowerPoint. Understand. Yeah, so this was supposed to be here. Just give me a second. I want to check and see if the most recent one is uploaded there. Doesn't matter. I'm going to go ahead and I'll update this later. I made some minor changes, but it doesn't matter. Yeah, so for example, I remember that I found a better example here and I put the fault recovery application here, but it's not here. That's how I found it. So fault recovery. So for space exploration, for example, what we do, we add modular redundancy. What it means is that we get the same data and we run the data on different kind of instructions, architectures that do the same thing. So these architectures are different, but what they do is the same exact thing. And then you add a loader kind of thing. Then you compare this output of different architectures to first of all, find the faults. Because if they have discrepancy, it means that there's something wrong. And somehow you can recover from that if you have, for example, 3 modules that do the same thing, and then you have a loader at the end. So even if one of them doesn't work well, the other 2 works fine, and then you get the correct output. So that's the best example for multi-instruction stream in single data, because you send the same data, and then you have different instruction sets to do the same computation, but the instruction set is different. One of them is using, for example, x86, the other one is based on MIPS. Instructions are different, the output is similar. Very uncommon architecture. Then we have the multiple instruction stream and multiple data streams. So most of the modern processors are, they belong to this category. Multiple instruction stream, multiple data stream. We have superscalar processors, for example. We have Intel Core i7 that has multiple instruction stream and multiple data streams. So the focus of our class is on single instruction, multiple data, SIMD, and multiple instruction, multiple data stream, okay, MIMD. We don't talk about this much here. I used to work on these topics. That was for a NASA project, but we're not going to talk about it now. It's a little bit more advanced. And single instruction, single data, we already talked about it. This is the typical MIPS processor that we covered. Okay. So now let's start with the first advanced architecture, which is the vector architecture. So the vector processor architecture is a single instruction, multiple data architecture. It belongs to the second category that we talked about. What it does, every time we want to run an instruction, it goes to the memory and brings a chunk of data to what we call vector registers. And then we put them in the register files, and we do operate the same kind of instruction on the whole chunk of data that we bring. Okay? And when the computation is done, we store it back to the memory. So we have an instruction set architecture called VMIPS, which is a vector MIPS processor. And it also has scalar, and the scalar part is similar to the MIPS. But it also has the vector kind of instructions, which makes it a vector processor. So this architecture that you see here is a very basic vector architecture. Now we're going to go into details of every component of this architecture to know a little bit more about that and see how it works. So now let's start with the first block, which are the vector registers. So looking at this architecture, this is scalar registers. We already know about them. These are the 32 floating point, 32 integer instructions that we covered in the MIPS. The vector registers are here, and we usually have in the VMIPS architecture, we have 64 elements or 64 registers. So So each of these registers are used to store an element in the vector. And they are 64 bits wide. So this is what we add to the MIPS architecture that we had before. We have vector registers that have 64 elements in it, and they are 64 bits wide. They are 64 bits wide because we want to cover the double precision floating point computation. Right? So we're not going to use 2 registers, similar to what we were doing, as opposed to what we were doing in the scalar register, that we were using 2 floating point registers to do double precision floating point. Here we have a single register supporting a double precision floating point number. And obviously when we have this vector register, we should have enough ports to support moving data from vector registers to vector functional units. Right? So this is about the data bus and the vector ports and everything. So the second component are functional units. So you can see these are the functional units in the VMIPS architecture. So these functional units, they are fully pipelined. It means that we can execute each one instruction in one clock cycle. It's completely pipelined, but they also obviously they have dependencies. So when we have dependencies, we can't do it. But it's designed, it's fully pipelined such that we can execute one instruction in one clock cycle. So we have, obviously we have a control unit, therefore we need to check the control hazards. We have here we can actually get structural hazards. So in the vector processor, we mentioned the MIPS is designed in a way that we don't get a structural hazard, but that was only for single instruction, single data. In case of the vector processor, you might get structural hazards, and that's because of not having enough registers, the vectors being too big, and so on, right? All right, and as you can see here, the functional units in the VMIPS architecture has 5 blocks. It has floating point addition and subtraction block. We have floating point multiplication, floating point division, and then we have integer and logical operations. These are the 5 blocks that we have in the functional unit for VMIPS. Again, to emphasize one more time, these are scalar registers that we have. We see here. These are the things that we already had in the MIPS processor. Okay. So as you can see, there's another block called vector load store block. So this is responsible for moving vectors from memory to the registers, and vice versa, moving data from registers to memory when it's needed. Okay. So as you can see, this entire process is fully pipelined. It means that we're going to have an initial latency to get the first data from memory, but after that, we can move data from memory to the register file every clock cycle. Right? This is a pipeline structure, we're familiar with that. So this vector load and store unit is responsible for handling the load and store operations. The same unit can also handle the scalar values. Some terms that we keep using here and I didn't use before was when we say scalar processor, it's a MIPS processor, so it just has one integer operation, and it doesn't have to be an integer operation, it can be floating point, but scalar versus vector. So vector means that we bring a bunch of data, scalar means we bring just one single data, we work with a single data. Okay, so now let's okay, can you guys give me a few seconds? I want to download it from Google Drive because I updated all these slides, so I don't want to have the old version. So we can have it. Give me a second, I'm going to download it from Google Drive. Go ahead. Yeah, my bad.
Not the worst thing, you know? I think the worst thing I ever witnessed was wait, I put the wrong final on Blackboard.
Okay.
And then the mass email of like final 1 in parentheses underscore final or something.
Okay, that's
do this one, guys.
That's not fun.
Like, kill it.
Two-step verification is not working fine. Never mind. It's not a Google Cloud either. It's on my day. Alright, so we continue. Yep. Scalar registers. Sorry. Yeah, scalar register. So this box is supposed to be here. We have scalar register will provide for scalar operations. We have integer operations and floating point operations as usual. It's a MIPS architecture. But it can also directly provide the addresses to the vector load and store block. So you can see that there is a path here, and this is used for calculating the addresses and sending it to the vector load and the store block to handle the vector operations as well. This is the same exact scalar registers that we have for MIPS. So we have 32-bit integers registers and 32-bit floating point registers, and 32 of them. And as you can see, so we have one input for the functional units. As you can see here, this part is not very different from the MIPS. I'm going to skip it. Now let's look at some samples of the VMIPS instruction set architecture. So if you remember, we had the add.d, for example, was for double precision floating point calculation for add. Here we have this vector letter here. It's going to say add VVD. It means that it's adding two vectors. We have add VS. It means it's adding a vector with a scalar value. It's double precision. So we can have some examples of it. For example, when we have add vv.d, v1, v2, v3, v1 is the destination register, v2 and v3 are the source registers, source vectors. So we have different elements from x1 to xn in the vector v2, and then we have y1 to yn in the vector v3, and we add these two element-wise and put the result in v1. This is how this works. An example of the scalar, vector and scalar operation is this. So we have f0. f0 is a scalar value. And now we want to add it with the vector. And as you can see, this is actually a subtraction when subtracted from a vector. So v2, if v2 has elements x1 to xn, v1, which is the destination vector, is going to have an element-wise subtraction of f0 from each element in v2, which is going to give us x1 minus f0 and putting the result in v1. Okay? is a sample of the VMIPS vector instructions. So now let's have an example and see how vector operations actually help us to accelerate the process or accelerate the code. So this is a very simple, not simple, well-known vector problem called DAXP. It's a double precision A times X plus Y. Okay, so it's like a multiply and accumulation operation. It happens a lot in machine learning. We are multiplying a number with input X. X is a vector, and then we have Y as another vector, and we store the result in Y. Okay, so let's see how we can do it if we have a scalar processor. We don't have a vector processor. So this is a scalar instructions architecture. So initially we get this value of scalar A that we have here from a specific place in stack pointer. So ignore this part because we don't care about it, but just focus on the loop. They get the value and put it in register F0. So moving forward, F0 is going to be my scalar value that I want to add with the vector. Okay. Now, if we don't have a vector processor and we don't have vector instructions as architecture, we have to work with the elements directly. We have to create a loop, and that's something that you're familiar with, right? You actually did vector multiplication in your project. So you have to create a loop, you have to read an element from the loop, and then do the process on that element, and then go to the next one, and so on. This is how you implement the vector multiplication. So we have it again here. We load the first element, then we multiply it by F0, which is the scalar value here, put the result in F2. We load the next value from the next vector, which is yi, and then we add the result of the multiplication, which is F2 with F4, put the result in F4, right? So that here we're done with the multiply and accumulation. The next steps are going to the next place in the vector, right? Because the double precision, we have to add it with 8. You're basically reading the next element. And we do the same thing for both vector x and vector y, and then we have a specific bound. In this case, it's like 512 divided by h. This is how many elements we have. We have 64 elements, for example, for this case. And then we have a branch. So repeat this process 64 times, so we can do 64 with 64 vector multiplication. Okay, this is what the loop does. Now let's say we have the VMIPS instructions as architecture and see how it works. So if we have the VMIPS code, we can see that we can load the scalar value to F0. Then we have an instruction called LV, which loads the entire vector. So you load the entire vector, that is the first element in the vector is added as an S0. And then you move the entire vector to V1. Okay. Now you multiply V1 with the scalar using the mul vs.d instruction. So this is handling the entire multiplication, vector multiplication. And then we load y vector. And then we use add v.d to add these two vectors. And then we store it back using SV instruction, right? So looking at this, we can see that we don't need to create a loop. We don't need to work with elements. We have instructions that work with the entire vector. Okay. So as you can see, the dynamic instruction count is significantly reduced. If we have a loop, we have to keep repeating those instructions in the loop to finish it. Here we basically have 6 instructions, 7 instructions. That's enough. Looking at the loop, just the loop, this part is just the initial load that we can ignore. This 6 instructions are the 6 instructions which we have to create a loop for here, as you can see. So the dynamic instruction count is significantly reduced because it's just one instruction. It does a lot of things for you. So in this example, we had 64 elements, but if we have a larger size, it only works with 64 elements, and then you might have to create a loop. This particular example, we have 64 elements, but if you have more of them, they have to keep doing it until we cover the entire range of the vector that we have. So, and the last thing is that we can see that the overhead instructions that constitute nearly half the loop on MIPS are not present in the vector code. What are the overhead instructions? Are everything we do here. The add I, sub, on side, branch not equal. Like everything we do here is just for handling the vector calculation. And you don't need them because the vector instructions and architecture automatically supports that. Okay? So we get rid of these instructions too. All right, so with this information, let's see what are the advantages of the vector processor over a scalar processor so far. Okay, based on what we just explained, what are the benefits of using vector processor compared to scalar processor? The first thing is, as we covered, when we have a single vector instruction, it has way more information than a scalar instruction. It's equivalent of an entire loop in a scalar. So it means that the instruction fetch and decoding bandwidth is going to be significantly improved. This is about just fetching and decoding instruction. Instead of fetching and decoding 600, 700, 1,000 instructions, we can fetch 7, 6, 10 instructions, and it does the same thing. So the bandwidth of fetching and decoding is significantly improved. Okay. The second benefit is when we are using vector operations, we are already telling the system that the computations within the vector, they don't have dependencies. So when you multiply the first element with the second element in the vector multiplication, by just using the vector operation, you're already transferring this information that the next multiplication is independent of the second multiplication. There are two different vectors. This is the kind of information that we don't have in the scalar processors. So in scalar processors, even if based on our code, every time we have to check a dependency, because we don't know beforehand that there is no dependency in this code. So architecture should be always designed for the worst case situation and keeps checking the dependencies. But when we have vector instructions, we're telling that at least within this vector size, we don't have dependencies in the instructions. That means that we don't have to have a hardware to check for the data hazards within a vector instruction. Okay, that's one benefit. Okay, so the next thing is about how we work with the main memory. Vector instructions have a clear pattern. We find the first element, and we know that, for example, for the next 64 elements, we have to move this to the register file, we have to move this to the cache, and so on. This is another information that we don't know in a scalar processors. For every block, we have to check the cache. But for vector operations, you have to bring a chunk of data to the register file and know that you are going to use that data. Okay, so you don't have to check cache every time. It's a better way of handling the memory hierarchy. At least for the next 64 elements, I know that I should just work with the register file. Don't have to go back and check the memory. Okay, so this is a better way of handling memory. It's going to lead to less latency and so on. Another benefit is when you don't have a loop. So for example, when we use a scalar processor to run this vector multiplication loop, we have to create a loop, right? When we have a loop, it means that there's a possibility that we can get control hazards, right? The whole idea of branch prediction. When you create a loop, you have branches, then you might have control hazards, you have to check for control hazards and so on. But when you use vector instructions, you can replace a loop with just vector instructions. Getting rid of the loop means that we don't need to check for control hazards, and we don't need to have a branch prediction block, right, for many cases. This is another benefit of using vector instructions. Now, something that is very important so far and we have to have this in mind, is that all these benefits that we talked about, which are the benefits in instruction bandwidth, the hazard checking, don't need to check control hazards, data hazards, and the efficient use of memory, these are the features that provide benefits for the vector processors. But with the information that I provided so far, we're not really doing any parallelism in the computation side. What it means is when we have 5 functional units, floating point add, floating point multiplication, integer, logic, and so on, although we bring the data, a chunk of data, to the register file, when it comes to the actual computation, we have to send one data to this functional unit, get the result, store it back in the vector register, and send the next one. So we do some parallelization in the data transfer, but we are not using parallelization in the computation side. Okay, so this could be a fallacy, but if you think, oh, just because I'm moving data to the register file, it means that I am also doing the computation in parallel, which is not the case. You can have a vector processor that is not parallel in terms of functional units. You still get some benefits, but you have to remember that these benefits are not because we improve the computation. It's because of all these things that we talked about. Instruction bandwidth is improved. We don't need hazard detection. We have a better way of handling memory. We do some parallelization in the memory side, the data transfer side. But the simple vector processor doesn't do parallelization in the computation side. So how do we do parallelization in the computation side? It's through adding something that's called vectoral veins. Okay? So one of the benefits of the vector computation and vector instruction architecture, as I mentioned, is that we already know that there's no dependency within the vector. And because there's no dependency within the vector, we can add computation lanes, something like this. We have 4 lanes, for example, in this case. And we can split the register across these 4 lanes. We have this vector register file, and we can split it between the lanes. And as you can see in this example, each lane holds every 4th element in the vector. So you have element 0, 1, 2, 3, and then you have element 4, 5, 6, and 7, and so on. So now, this is when you're actually parallelizing the computation as well. Before this, if you don't have multiple vector lanes, you're not doing any parallelization on the computation side. You're just using memory blocks. Okay? So this is the case that we have 4 lanes. In every lane, in this case, we have copies of the functional unit. So we have floating point add and floating point multiplication shown here, but you can imagine that we have all the other blocks too, integer, logic, and so on. Those 5 functional units that we talked about are replicated in each lane. So here we are adding hardware, obviously, but then we can use the parallelization in the computation as well. Now let's see how it works. If we have a vector processor that only has 1 lane, this is the left side. You can see that in every clock cycle, we can calculate 1 element-wise computation. So we have an addition, for example, here. In the first clock, we get C0, which is A0 plus B0. And in every clock, we have element-wise addition. And we need 10 clocks to finish this computation, for example. A0 to A9, B0 to B9. Now, if we have 4 lanes, we can get the C0, C1, C2, C3 in the first clock. In the next clock, we can get C0, C4, C5, C6, and C7. And in the third clock, you can get C8 and C9. So we need 3 clocks to finish this task, this vector addition. And we can do this because we already know there's no dependency between these guys. Okay? So this is a vector processor, and this is how it improves the process. Through memory bandwidth optimization, through instruction and decoding bandwidth optimization, and through removing some of the hazard detection blocks like branch prediction, control hazards, data hazards, and so on. Now let's talk about the next category of parallel hardware. This is called the Superscalar Processor. So the MIPS processor that we talked about so far is a scalar processor. The Superscalar Processor is a kind of processor that has copies of data path to execute multiple instructions at the same time. So this is an example of a two-way superscalar processor that you can see here. The two-way superscalar processor has a register file that supports two instructions at the same time. Then we have two ALUs and a data memory that can store or load two data values at the same time. So an n-way superscalar processor fetches and executes n instructions per cycle. So this is a more generic case, it's not two-way. But this adds some limitations, or we have to add some characteristics of the blocks that we have in the processor. Let's just start with the register file. We know that in a scalar processor, register file has 3 ports. It has 2 ports for reading the registers and 1 port for writing to the register file. We have some ports for addressing, but I'm just talking about the data ports at this point. If you have an n-way superscalar processor, you need to have 3 n-ported register file. 2n of these ports is used for reading registers, and n ports is used for writing to the register file. Okay. We also need to have n ALUs and n ported data memory, because we want to read n values at the same time, or write n values to the memory at the same time. So these are the modifications we have to make in register file, data memory, and ALU to be able to support an n-way superscalar processor. Okay. So now let's see how an n-way superscalar processor execute this code that we have here. So here we have 6 instructions. We have load word, add, subtraction, or, and store word. For simplicity, we are starting with a type of code that doesn't have any dependencies. Okay, so here we don't have any dependencies. It means that we can run every instruction in 1 clock cycle and we're fine. In the first clock, we run the first 2 instructions because it's a two-way superscalar processor. We have the load board, we get the 40 from the instruction. For simplicity, it's not shown here. The 40 is coming directly from the instruction encoding. And then we have S0 to calculate the address. For the next instruction, we have S1 and S2 coming from the register file. And the second ALU is going to do the addition. The ALUs are used to add for addition for both instructions. One of them is calculating the address, the other one is actually doing register operation. The top half of the data memory is used for load board. The bottom half is not used because add is not using data memory. Okay. Now both of these instructions are going to write something to the register file, and that's why the left half of this block is highlighted. For the next instruction, we can have subtraction and AND. As you can see, we can read the instructions. One of the ALUs is doing the subtraction, the other one is doing the logic AND operation. We don't use the data memory. Both of them write to the register file, so the left half is highlighted. And for the third set of instructions, which are OR and store word, we use S1 and S5. We use the ALU to do the OR operation, and then we use ALU to calculate the address for store word. The bottom half is actually working with the data memory. We're writing something to the data memory. And when it comes to the register file, the bottom half is not using it because we're not writing anything to the register file. But the top half, which is OR, is writing the result of the OR in register file, and that's why we have the top left side highlighted. So as you can see, we can execute 6 instructions in 3 clocks. This is the ideal case for a two-way superscalar processor. For an n-way superscalar processor, the ideal case is that we get 1/n CPI, or n IPC. Okay, that's the ideal case. If we can get an IPC of 2 in a two-way superscalar processor, we're good. That's the maximum speed that we can achieve, right? But that can always happen, and we know why, because there are dependencies, right? We have superscalar processors, and inside the superscalar processor, we want to execute codes that have dependencies. All right? So now let's have an example. So this example is an example of a different set of instructions. We have load word followed by an add, and then subtraction, and or store word. But looking at these instructions, we can see that here we have a dependency. It's a read after write dependency, right? We load something T0, but we want to read the same T0 register for the next instruction. Looking at the subtraction and instructions, we have another read after write dependency here, and another read after write dependency on these two instructions. So right now we have these dependencies, and we want to see how the two-way superscalar processor is going to work when I want to run this kind of program. So we already know that when we have an ALU operation followed by load word, even if we have forwarding, we have to delay, we have to stall the pipeline. Right? You remember that, right? So when we have load word, forwarding is not going to fix the problem. Because data is going to be ready at the memory stage. We have to stall the pipeline no matter what, and then we can do forwarding. Okay. Because we have this limitation, it means that if I want to run the load word in this cycle, first of all, I can't run add at the same time. That's obvious. That we already know. We can't run add at the same time because of the dependency. But we can't run add in the next instruction, next clock cycle either, because of this kind of load word and ALU dependency that we have. And that's when we have to stall the pipeline. This is where we stall the pipeline. We run the instruction, first clock cycle, we run this load word, then we stall the pipeline, and in the third clock, we actually run addition. There's no dependency between add and subtraction, so we can run both of them at the same time in the next clock. In the clock after that, there's a dependency between AND and subtraction, but we know that if we have forwarding, that dependency can be resolved through forwarding, if you have forwarding hardware. So AND and OR instructions, which don't have any dependencies, can run in the next clock cycle, and then we finish the computation running store word in the clock cycle after that. So how many clock cycles we need? We need one clock cycle for load word. Then we have to stall this pipeline, that means another clock cycle. Then we run add and subtraction in the third clock cycle. We run AND and OR in the fourth clock cycle. And we run store word in the fifth clock cycle. Right? So what is the IPC for this one? Can we calculate the IPC? How many clocks we need for running the computation? 5 clocks. How many instructions do I have here? Which means the IPC is going to be 6 instruction and 5 clocks. 1.2. Right? So 6 instruction, 5 clocks. So this is far from the ideal 2 IPC that they want to get. Best case scenario of IPC of 2 for a two-way superscalar processor. So how can we solve this? You already know the answer. How can we solve it? Mason, do you have an idea? No.
Scheduling?
Scheduling. Okay. Reordering. So if we reorder the instructions, we should be able to fix this. We already know this from even the Scalar processor. So now I'm going to call, just for this module, moving forward, I'm going to separate the terms scheduling and reordering. And that's because scheduling is also used when you want to schedule an instruction in a superscalar processor to different ways that you have, to different lanes that you have. So let's call that a scheduling, and let's call changing the order of the instructions reordering. So we're going to use reordering. Okay. It's also called scheduling, it's just for us. Makes it easier moving forward. Okay. So now, when we want to reorder the instruction, it means that we have an out-of-order processor. We keep adding terms, right? So next time that you're seeing a data sheet of the processor that says it's a superscalar out-of-order processor, you know what it is. Superscalar means that we have multiple lanes. Out-of-order means that it has the capability of going ahead and checking the instructions and change the order of the instructions to remove, but not remove any stalls, is to benefit from, not benefit from, but changing the instruction. Instead of just stalling the processor, we can run an execution that doesn't have, or run an instruction that doesn't have any dependencies. Okay? All right, so we have an out-of-order processor. Let's see how it's going to help us. This is the code that we had for a two-way superscalar processor. This is from previous slide. We saw these dependencies. T0, we have a read after write dependency here, another read after write dependency here, another read after write dependency right here. So now let's see what can we move around to fix this problem. So we start with the subtraction. So subtraction is saying S2 subtract S3 from S2, put the result in T0. One candidate is moving subtraction before add. Can we do it? Why can't we do it, Brendan?
Because add uses T0, so you'd be using the wrong data.
Which is called what kind of dependency?
Read after write.
Write after read. So it's a write after read dependency, right? Because of the write after read dependency, we can't move it before the add instruction. Okay, now let's check the next one. And. Can we move and before add? No. Any ideas?
Let's just quick.
Andrew?
You said and before add?
Yeah, can we move and before add?
No, just the T0 is going to be different.
We can move it, and this is not because of a write after read dependency, because these two instructions are stuck together. If I move this one, this T0, it has a read after write dependency, but not to this instruction. It has a read after write dependency to subtraction. So this instruction has to go after subtraction. Right? Although there is no dependency right after read dependency, it has to go after subtraction. So these two instructions are stuck together. Okay? So how about OR? Can I move OR S5, S6, T3 to here after load board? Sarah, yes? Yeah. We can move it. So now the next question. Does moving it here in a two-way superscalar processor is going to fix the problem? Like, not, is it going to fix the problem?
Well, I feel like it's not actually going to help the stalls, right? Because it's the other part of the processor sticking at a command.
We can move OR here, but when we have a two-way superscalar processor, it's going to execute both instructions in one clock cycle. Now, still in the next clock cycle, we need add. Right? So so moving this is going to help us to use the two-way superscalar processor better, but still we need to stall. Right? Still we need to stall. Because these two instructions are going to be executed in the first clock cycle, and then when it goes to the next clock cycle, we still have dependency. Right? Okay, so what should we do? What do you think we should do? Go ahead.
Yeah. Enable the variable to move the dependence.
You want to change the variable? So it's a little bit difficult to come. I mean, if I don't explain it, it's hard to just come up with it, because I can tell you the answer is not optimal. That I can tell. Practically, you can't get an IPC of 2 with this way. You can reorder them. You can get some improvement. You don't need to stall it, but still, you can't get IPC of 2. Why? Let me show you why. So I move OR here, and I do something a little bit more creative too, is moving store ward after that too. But this doesn't have any dependencies either. So I can move a store ward up there too, and it doesn't change my code. But what I do is that in one of these clock cycles, I don't fully utilize the two-way superscalar processor. So in the first clock cycle, I'll run load word and OR. Okay. In the next clock cycle, I just run a store word, and that's it. So you run something, but you don't use the full capacity of the two-way superscalar processor. There's a read after write dependency here, but we know because this dependency is at the ALU stage, one clock cycle would be enough to fix the problem. A mistake would be running load word in the first clock cycle, and that's it. And then we can't use run OR and store word together because of that dependency. So basically, you have to run OR with load word. It's not just a choice, it's not an option. You have to run OR with load word to fix this read after write dependency, because we can't run these two instructions at the same clock cycle. But we don't need to stall for that either. It just needs to go to the next instruction, next clock cycle, that's it. That would be enough. Because we can forward it from the ALU stage. So you run load word and OR at the same time. This way you fix the problem with the read after write dependency that these two instructions have. Then you run the store word in one clock cycle. Don't use the capacity of the two-way superscalar processor. And after that, you can run add, which has a read after write dependency to T0 to load word. But because there's already one clock delay, we can do it. We can forward it now. So instead of just installing it, we are running the store word instruction there, and so on. So then we have an add of subtraction. Then at the end, we have add, which also doesn't use the full capacity of a two-way superscalar processor. So can you tell me what the IPC is here? 1.5. Which is because we have one clock cycles here for these two instructions. One clock cycle here is actually not 1.4. Yeah, it's 1.5. We have one clock cycle for store word, another clock cycle for add and solve, and one clock cycle for AND. That means we have 4 clock cycles and 6 instructions, which gives me the IPC of 1.5. It's good, but it's not 2. Okay? Now, what we can do is this is just a reminder that when we have anti-dependence hazard or write after read hazard, it is usually caused because of the programmer choosing to use the same register for 2 different instructions when they didn't have to. So if you use 2 different registers, some of these problems are going to be resolved. And that's the technique that we're familiar with, register renaming. So we still can't do register renaming. Register renaming can help us to get rid of some of these write after read dependencies. For example, if we had register T4 in the subtraction, then it would have been fixed. There was no need to use T0 here. The fact that they used T0 caused this write after read dependency, which was causing problems for an out of order processor. If we had an in order processor, we never had an issue. Because in order, the processor can't even change the order of the instructions. A quick reminder. Okay, so register renaming for the Superscalar processor. So let's go a little bit more advanced. For register renaming, we can either use the registers that we haven't used before, or in many real case processes, they have some registers, like register 0 to register 19. Let's say we have 2 registers in MIPS for register renaming. So 20 registers. So these 20 registers cannot be accessed by the programmer. It's something the compiler uses to do the reordering here. Okay, and registers are called R0 to R19. Right? So now let's see how register renaming can improve the execution time of the program that we had. This is the original code we had. And now what we need to do, this was the subtraction that was causing the problem, read after write issue, right? So now let's change this T0, which was the reason that we had this write after read dependency, to R0. And obviously because we changed this to R0, this should change to R0 as well. Because we want to use the output of this instruction in the AND operation. So now let's see how we can reorder it. If I just change it to R0, now I can move the subtraction before add, and also I can move AND before add, and OR before add. So everything can move before add without any dependencies, because I got rid of the write after read dependencies. Now I can run this instruction. I can run load, word, and subtraction together, and then I can run AND and OR together, and then add and store word together without any dependencies, which gives me the IPC of 2. This is how register renaming can fix a lot of these issues. If we have write after read dependencies, we use register renaming, and then we use reordering to maximize the IPC that we can get. Right? Any questions?
So the second part says that the processor is free to use to eliminate hazards, and you're saying that programmers don't have access to it. So is it done in the hardware or?
Compiler level. Usually it's at the compiler level, so it does the reordering. It knows that you have this capacity of the registers. When we say the processor is free to use it means that there are some registers in the processor that can be used to fix this problem.
So,
but who uses that? Compiler, if designed well, compiler can take care of the register renaming and reordering.
So as far as I understand, if a compiler can use some registers, then anybody who writes the assembly can also use the registers.
That's true. So if a compiler can do it, but maybe it's a better thing to say the assembler, right? Because we have different layers. So compiler, like the entire stack. So assembler, when we do machine code, then we can add some features to that. Or the processor can do it itself too. Right? It's a very easy thing to do to find the write after read dependencies. So we can just check write after read dependency, and every time that we see that instruction, we just use a different register. So we change the machine code basically, right? And that's why assembler can use it. Machine code is when we address different registers, but every time we find a dependency, we change the machine code and use it to R0 registers, for example. That was a good question. Okay, any other questions? Good. Okay, so now let's talk about the loop example and see how we can execute this loop on a superscalar processor. If I want to design a question from this module that combines what we learned in module 7 about register renaming, unrolling, and so on with the superscalar processor, that's what I can do. That's a good example of a question that I can design for the final exam and the qualifying exam. Okay. So now let's see, we have this loop. This is a very basic loop for simplicity. I just use integer now. I don't want to combine it with floating point. It's just integer instructions. So this is the loop I have in MIPS, which is equivalent of this loop in C, for example, a high-level language. Now, okay, I want to show the stalls. So we have these dependencies that we can see here. We have a write, we have a read after write dependency. This is an add instruction coming after load word. We know that we need to stall, right? So we have to stall it as you can see here, and everything else we can execute and we're fine. Okay. So this is fine. There's no dependency here. So we want to write it back to the register 5. All these operations happen at the ALU level, so we're good. If we have forwarding, we just need a single stall between load word and add unsigned. Okay. Now, so let's see how we can fix, if we want to do reordering here, how can we fix this add? This is stall. How can we move one of these instructions to the stall and take advantage of that stall? So add unsigned, there's dependency, obviously there's something, we need an instruction going before that. Can we move the store word? No, why?
It's supposed to be storing the value that the add creates.
It's supposed to write the value of T0, the result of add unsigned, to this address. So we can move that. Can we move add immediate? Regina, you already found this issue. Can we move add immediate here? Can we? No. Why can't we?
Because we are using S1 for store. So if you use add immediate there,
Yeah.
you can change the value.
That's right. So that was in one of the slides. I didn't want to go ahead of myself at the time, so we removed that slide to remove the confusion. So if you move add immediate here, then when we go to store word, we're changing the address to S1. So we're locating a different address, and that's going to cause a problem.
Are we allowed to change the number on the store word?
Yeah, and that's how you fix it. So if we move add immediate here, and we change the offset, we already know that, but now you have this information. At the time we didn't have this information. We already know that when we do loop unrolling changed the offset of load word and store word, right? That was part of register renaming, reordering, and so on. So we already know that we have access to the offset of the store word and load word. So now it gives me the possibility to move add immediate here and change the offset of the store word. Blake, what should be the new offset?
-4, right?
What should be the 4, right? Sorry? What's your name?
Salman.
Salman. Sorry. Close. So that's right, Salman. So we have to have offset of 4 because we have add immediate S1, S1 minus 4. And if you have an offset of 4, it's as if you have an offset of 0. Right? So this way, there's a right after read dependency. It gives us 0.83 IPC. But then we fix it that way, then this is the case that we were looking for. Right? We're getting an IPC of 1. So far, we're not talking about Superscalar. It's just the scalar processor running this code on it. Okay, now let's see how we can schedule this to run it on a superscalar, a two-way superscalar processor. That's why I say use a different term, because we use scheduling for scheduling the two-way superscalar as well. So how can we schedule it? We can run the load word in the first clock, and then we don't use this second way here, and that's because of this dependency that we have here. So I can theoretically I can run add I in the second way. It's not going to cause any problems. But then I have to stall the next clock cycle because of this add-on sign. If I don't install it, because of this dependency, read after write dependency between load word and add-on sign, we need one clock between these instructions. So you either can use the full capacity of a two-way superscalar processor and put add I here, and then no operations and no operations in the next clock cycle, or you can run load word and then add I and then add on sign. Okay? But the other limitations that we have here, we cannot run add on sign and store word together because we need one clock delay between these guys. We want to do the add operation and then store the result. right? So these two cannot be executed in the same time, but the store word can be executed if branch not equal. So we have 1 clock for load word. If I give this question in the exam, if you put add immediate here, you get the full 0.2. It doesn't matter. Okay, you can schedule add immediate in the first clock cycle, but then you have to have a no operations here. Add on sign, no operation, store word, branch not equal. So what is the IPC here? How many instructions do we have?
5.
5 instructions. How many clocks? So what is the IPC in?
5 over 4.
It's 5 over 4, 1.25. Okay. So now, let's do the last, oh, your overtime. Okay, I can quickly cover that and I go back to it. Give me a minute and I do want to talk about it. So we have, if we unroll the loop, and I'm going to cover it in the next session again, we can unroll this loop. Let's look at the factor of 4. We already know how we do the unrolling. When we unroll the loop, we're going to get a lot of dependencies here. This is the part that we already know. When you unroll that, then you want to use register renaming to change those registers such that we can't get this much dependency. Okay, so register renaming is going to change these T0 registers to new registers, R1, R2, R3. And after that, we can reorder them. How do we reorder them? We do all the load words in the beginning, and then we do the add-on sign, store word, add immediate, bring any. We change the offsets, we change the add immediate. We already know this. Now, if I want to schedule this in a two-way superscalar processor, I can group every 2 instructions without any dependencies. I have load word for T0 and load word for R1. And in the next clock, I want the next 2 load words, load word R2 and R3. Here, when I want to do the add on-sign T0 and S2, there's already 1 clock between load word and add. So I'm good. Same story here. When I have load word R2, there's already 1 clock between load word and add on-sign here. And store word and add by and branch not equal. What is the IPC here? I have 14 instructions, 7 clocks, IPC of 2, the best case scenario. Okay, thank you guys.